Here's a poinsettia leaf. The red structures here are actually leaves. We may think they're flowers, but they're actually leaves of the poinsettia. And they're used for attracting pollinators the same way that a flower actually is. And then you've got or plants like the Venus flytrap there that actually uses its leaves, it's just a modified leaf, to catch bugs, to catch prey. So those are all similar structures. They all come from the same basic tissues, they all develop the same way, but they develop into different things. But they're all the same because they all share common ancestry. All right. Now, here we've got, this is a mammal. I'm sorry, this is a reptile on the left and a mammal on the right. Mammals, you may know, like us, we have 3 bones in our ear that help us hear. Reptiles only have 1. Now, what was recently discovered was that our other 2 bones, the green one is the one that's conserved in both, the yellow and the blue are actually found homologous bones in the skull and the jaw of the reptile. And that those, in humans and other mammals here, have actually developed into 3 bones, more homology. All right, next, we've got analogy. Now, analogy is sort of the flip side to that coin. We've got some different organisms have actually developed different ways of doing the same thing because they don't share an ancestor that had those same structures. So, look again, we've got more wings here. We've got the bird again. But you'll notice that the bird and the bat, while they do have similar bones, they're actually rearranged and they're different because birds and bats did not evolve flight from a common ancestor. They evolved it separately. So they have it developed differently. Same with a pterosaur. This is obviously an extinct animal, but its flight completely different as well. And it's not just the bones, but actually the whole flight structures, the muscles, the muscle attachments, and then a lot of the other skeletal parts are quite a bit different. And then the insect, of course, that's a damselfly wing up there. Totally different structure because, again, it doesn't share as close a relative with these vertebrate animals. All right, next, more analogy. We've got pandas. Pandas actually have a structure that we call a thumb. It's this 5th digit out here. It's not this. Don't worry about that. That's a wrist bone. The forearm actually connects to that. But this is their thumb, and it's sort of opposable like ours. But if you count these, you've got 1, 2, 3, 4, 5, 6 bones here, 6 fingers. Well, this one is actually not the same as our thumb. This one is, the blue one. This is a wrist bone that has evolved to serve that same purpose as our thumb, but in a completely different way, because again, panda and human ancestors go way, way back, long before our thumb or their thumb developed. All right, next. So here's a simple, well, here's a little joke. But homology, you've got these 2 sisters. They're similar because they have common ancestors. They got the same parents, so they've got some similarity. Then you've got these 2 Elvis impersonators here who are more like an analogy. They have similar structures, similar characteristics, but they have developed those jumpsuit and the hair and the little capes to serve the same purpose, and that, of course, is to be an Elvis impersonator. More evidence. We've got vestigial organs, and atavisms. Now, we can make predictions about vestigial organs. When we see them, we should be able to say that that is an organ that relates somehow to that animal's or plant's ancestry. So we've got kiwi, which is a bird. It's found in New Zealand. It's a little guy like this runs around the ground. Completely flightless, has these stubby little wings. Pointless organ on that bird. Doesn't use it for display, doesn't use it for hunting food or any other reason. They're just there, and they're there because that bird's ancestors were flighted. They didn't have a need for flight. Eventually, they evolved smaller and smaller wings. But they still have them. They're vestigial. Here's a blind cave tetra from Africa. Has eyes, but early in its development, its eyes grow a layer of skin over it. It lives in a cave. Doesn't need to be able to see anything. There's no light to see anything with anyway. So it's lost that ability to see, but it still has eyes. Goosebumps on people. I don't know how you can see that. We get goosebumps when we're cold. Our ancestors were hairier, and fluffing up that hair provided a layer of air underneath it for insulation. We have no need for goosebumps. That reaction to cold is completely vestigial. These last molars, the wisdom teeth, again, vestigial. A lot of people, most people who get them, they have to be removed because they're actually painful and damaging and can cause a lot of problems. And then you've got what we call atavisms, which are, once in a while, that vestigial organ will turn into, will start to show some of its ancestral state. This is a dolphin. This is the back half of a dolphin. I don't know how well you can see it, but there are little legs sticking out of that dolphin right there. And those legs have bones, and they can actually move. Now, obviously, a dolphin doesn't need bones, but the theory of evolution, it doesn't need legs, but the theory of evolution says that its ancestors did. So it still has a pelvis, it still has rudimentary bones in that area, and it still has the genes to produce legs. Once in a while, a mutation turns on those genes. Same thing happens, you hear about people who are born with tails, babies who are born with tails. And there's a few different ways that that'll happen, but sometimes it's got bones, it's got muscles, and it can be moved around voluntarily. And that's because, same basic thing, it's an atavism. We don't need a tail, we don't generally have a tail, but our ancestors did. All right, next, biogeography. Now, biogeography is basically just a way of saying where organisms are found in the world, and the study of that. So, here's an example where we've got lemurs. And there are 99 different species of lemurs and their allies that are found on this one little island, actually a very large island, off of Africa called Madagascar. Now, you don't find lemurs anywhere except for Madagascar. You don't find any of their closely related relatives anywhere except for Madagascar. The reason for that, according to the theory, is that they had a common ancestor that arrived there, and then they speciated and radiated just on that island. Of course, they didn't leave the island, they had no way to get off the island, it had separated from the mainland there, and you only find those there. Now, if we found lemurs scattered around the world in no sort of discernible pattern that related to the theory of their common ancestry, then we would have a challenge. We've got marsupials, similar story. We've got, most marsupials, as you know, live in Australia. We do have a few marsupials, like our little possum friend here that lives in our neighborhood in North and South America. But when we look at that possum, the opossum, that's actually a very different family of marsupials than the ones that are found in Australia. And we can actually trace back how far that one is removed from the ones in Australia and see that it's removed basically at the same time as the continents separated between those two land masses. Again, this is something that you wouldn't necessarily predict without looking at common ancestors. Next. Honey creepers. This is Hawaii, and these are a variety of birds, all different colors, all different sizes and shapes, all found in Hawaii, all found in these little islands that didn't exist more than a few million years ago. And we get a small little population of an ancestor species that lives on these islands. They've radiated out, and we get all these animals are actually related. And they've been sequenced, their genomes have been sequenced, and we can see just how related they are. And they're all related to each other very closely and distantly from their closest relatives on the mainland. Again, not what you would predict if we didn't have some common ancestry going on. Next, molecular evidence. This is where it gets into the stuff that 150 years ago when Darwin and Wallace were writing, they never could have imagined. Their predictions, their theories have been backed up. They haven't changed. They've been modified and adapted. But the big pictures of them have been backed up and supported over and over again by technologies and sciences that didn't exist in their time, like DNA evidence. Now we can look at these animals here. This is just a tree of animals. Excuse me. We can look at this tree of animals, and this tree is built based on their genetic similarities. We look at their different regions of their DNA, see how different and similar they are, and built this tree based on that evidence alone. Now, that tree is great for that. We can take a look at that and say, okay, well, that just shows how similar their DNA is. And that's true. But when we look at other evidence, other trees that we build through other means, they all match up. And that's not a coincidence. It didn't have to be that way, but it is that way. And the reason it's that way is because it's all pointing back to the same